So yesterday in the last class we have discussed about the perceptron. A perceptron is a small neuron. It takes the input and output by taking the weighted sum as an input, and it transforms the data, that weighted sum, to the function. It is called activation function, like this. Suppose this is the neuron. It takes some input from the data set here. This is the data set. Okay, suppose if there are three columns data, that means three features, record 1, 2, 3, 4, 5, like this. Okay, if the data is here, attribute 1, attribute 2, attribute 3, then you will have these three input neural layer here and one output. This process is called here, this process is called a perceptron. Suppose it takes the input here and it sends this to this one, and from this, and from this, and with some weight 1, weight 2, weight 3. So suppose this value goes to this first input neuron and second input neuron, and this is a third input neuron. Suppose assume that it is 2, it is 3, it is 4, and the weight is suppose 1. This is 2. Suppose this weight 3 is, assume it as again 1. What happened? The weighted sum is equal to, generally it is denoted with the sigma of Wixi. So it means this value is 2, this value is 3, this value is 4. So 2 into 1 here, like this. Okay, 2 into 1 plus 3 into 2 plus 4 into 1 here. So 4 into 1. What is the total sum? 2 plus 6 plus 4, it is 12. So the input for this neuron here is 12. So this goes under some activation function. That activation function may be a step function, sigmoid function, logistic function, ReLU. Okay, all those, these are all called the activation function. Suppose this step function says that this one, okay, f of x is equal to 1 if this is positive, the weighted sum. Okay, this is a weighted sum. Anyhow, for any perceptron, there will be one bias neuron also. This is bias neuron. For each neuron, you will see a bias neuron in each layer. So here it is also connected to this one.
The person is waiting.
Here, always the bias neuron is connected to each layer neurons, and its input is always 1, and weight you can take anything. Like suppose if I am taking suppose 4, what happens here? Based on this formula, Wxi we have calculated, and this Bi. The Bi is minus 1 into this weight, it is 4. So minus 4, it is a minus 4. So this is 8. 8 is greater than 0, so it is positive. The output comes from this neuron here is a 1. Okay, if this weighted sum, this one is other than 0, less than or equal to 0, this value, the output becomes 0 here, 0 here. So like this, the perceptron calculates the output either 0 or 1 using this step function by taking the weighted sum as an input. That weights you can choose randomly initially. So the initial weights are the initial weights are what? These are randomly chosen. Okay. So the randomly chosen weights may be between -1 to 1 initially, and there is a lot of processes, theories are there how to initialize your weights, the key initialization. Okay, different stories and theories are there. Based on those, you can, if the network is big, you have to use a He theory, HE. Okay, He initialization theorem is there. Based on that, you have to choose the weights here. Okay, this is the concept of the perceptron. This one. Okay, so what is their initialization? Set all the weights wij to a small positive or negative values randomly, and then you train all these weights iteration by iteration for a t number of iterations, okay, until all the outputs are correct. So if there is an error between the output, suppose here in the previous one, this is the input, and assume that this is the corresponding output here. So for 2, 3, 4, assume that the output is suppose some 10. And what happened here? The output here, we got it as 1. Okay, anyhow, when you check the step function here, this may be either 0 or 1. 0, suppose 1, 1. So here 1 is there, so the error is nothing. It is correct. But when you go to this second one, third one, fourth one, there may be differences. So those differences generally called the errors. So when the errors occur, you have to further iterate this process. What is that process? Updation of the weight process. So for each input vector, what is the input vector here? This 1, 2, 3, 4 here in the table. This is one input vector, second input, third input vector, fourth input vector. So when you feed these values into these neurons, okay, input layer, you will get a output. Similarly here, this one, okay, this one, and then this one. So when you keep this one, you will get one output. That output will be checked with this output, actual output. And if there is a difference, we update it. If there is no difference, we proceed for the next one. So like this, you can update your weights here by checking the input. So for each input here, for this each input vector, compute this activation of activation of each neuron J using the activation function G here. What is that Yi? This Yj, that means output at the jth neuron is equal to the activation function of sigma of all this weighted sum. Here we did not use this bias, but you have to add the bias also. So this becomes 1 if this is greater than 0, and if it is 0 if it is less than or equal to 0. And update this each weights whatever you have initialized here. So in this initialization part, with this formula in this perceptron. So in perceptron we use this formula to update the weights. What is that formula? Wij minus eta into yj minus tj and xi. What is this wij? The wij is the present weight will be updated by deducting this eta means it is a learning rate into this yj is a predicted value we have predicted here as a 8 here, okay, 1 here, 1 here. So and what is the actual value here? This is the actual value is also 1. So this is the predicted value minus tj is the actual value into xi. What's the input for this? Okay, for that corresponding uh, weight. So how many weights are there here? This is one weight, two, it is three, and four. Even this one also, W naught. So these four weights you have to update based on this. Assume that first we'll update with this one by checking a learning rate is 0.5. So what happened for W1? So W1 is updated like, what is W1? The W1 initially it is 1. 1 minus eta, assume that the eta is 0.6 into what is the original value? Predicted value is 1 by this network, and actual value in the table is also 1 output value into this xi. What is that corresponding xi is 2 here, this part. It is a 2 here. So this is 2. This becomes the entire becomes a 0. So the weight will be the same in this case. Similarly, if you want to update here, whatever it may be, this part becomes a 0 here. So the weight values will be the same. So if there is any difference
Excuse me,
here,
sir. Some others are
yeah,
waiting in lobby, so please allow them.
okay, from tomorrow onwards, I don't allow them. Okay, I have to join by the time. Remember that.
Okay, sir.
Okay, only 5 minutes are accepted. Okay, other than I don't accept it. Okay, remember it from tomorrow onwards.
Said I joined, but from the mobile, but I disconnected it.
Okay, every time this is a problem. Okay, don't join by mobile. So here, I hope all of you understood what is the process goes into this updation of the weights in the perceptron. Okay, so the perceptron uses only the step function as an activation function, and this is another important thing here. Okay, this is the important thing. Okay, how to update this weight. And how to calculate this recall here? Compute this activation of each neuron J using this. Okay, and then we go for one simple example here. Already, I hope I have calculated all of these. Okay, this is a XOR. Okay, assume that is it XOR? OR gate. So here 0 0 it is 0, 0 1 it is 1, 1 0 it is 1, and 1 1 it is 1. So these are this OR logic. This for this OR logic, you just update the weights to get the correct outputs using this network. So this is one of my network given. Already we computed this one. We updated these weights. Okay, so what is the first input? This is the first input, and this is the output target value. So what is this here? Now it is 0. Okay, this is 0 now. This value is also 0 now. Always the bias value is -1 here, and I have given W naught as this is minus 0.05, and this is minus 0.02, and this is 0.02. So what is the weighted sum here? W I X I plus beta, B well. So here the weighted sum here is equal to, this is -1 into minus 0.05. Okay, this is the first one here from this, and then from this here. So it is plus 0.0 into minus 0.02 plus again 0 into 0.02. So this two becomes 0, and this is again 0.05. So this is the weighted sum to go for this neuron. What is this neuron uses? This neuron using just a step function as we mentioned before, because this is a perceptron. So you should use this step function. Now you check whether this is greater than 0 or not. If it is a greater than 0, the output will be 1. Okay, if less than 0, the output is, so the predicted value here is 1, but the actual value is, this is 0. So how to update this weight here? So what is the first one? W naught. You update this W naught here. So the W naught, the original value is minus 0.05. Okay. Minus eta. You take the eta as 0.6. 0.6 into what is the target value? And this predicted value is 1, and target value is 0, into the corresponding xi is -1. Xi is the input here. So what happened here? This W naught becomes now, as it is minus 0.05 minus, this is 0 minus of minus here. This is 0.6 into -1, it is -1. So this becomes plus 0.6. So now this W naught becomes 0.6 minus 0.05. What happens? 0.55. 0.5. So this is the new weight now. Similarly, you have to calculate W1 also. What is W1 now? Anyone can tell me? What is W1? The original initial value W1 is 0.05. So W1 minus this predicted value is, what is the predicted value? 1 minus 0. Eta is 0.6. Okay, eta into this minus this into its corresponding input. The input is 0. So the entire thing becomes a 0. So W1 will not change here. So, and again, what is W2? W2 is also same thing. W2 is 0.02. This is minus 0.2. It is 0.2 minus of 1 minus 0 into 0.6 into its corresponding input. Here is this. Okay, so this becomes as 0. The entire thing becomes 0. So this. So now, what is the new weights, updated weights? W0 is equal to 0.55 and W1 is equal to same thing minus 0.202 and W2 is equal to 0.02. This is the weighted sum, right? Now we use these weights to update, to calculate the outputs. Now feed this second input here. This is 0 now. This becomes 1 now. This becomes 1 now. Okay, this is same. And now this weight is not 0.05. This weight is 0.55. So I use this minus 1 into 0.55 plus 0 into 0 minus 0.25 like this. You can get some value. If that value is greater than 0, again you will get the output as 1. Otherwise that becomes 0. And if there is a difference here, you update the weights. Otherwise you proceed to the next one. This is the procedure of this one. Okay. So now I have iterated 2 times now. These type of weights updated here by using the learning rate at 0.25, but the previously here I use the eta is 0.6. So that's why this is the difference. So now you can check it. The original values are here. W0 is minus 0.05. W1 is 0 minus 0.02. W1 W2 is 0.02. But now after updation, this is 1, this is 1, this is 1. Again after updation, you got this one, and this one. Still, you can proceed if the target value and output value, predicted value is not equal, then you can consider any number of times. Okay, that is about a single perceptron. Now the multi-layer feed-forward neural network is this. Here, at least, if there is at least one hidden layer involved in your network, that type of network is called multi-layer perceptron. So we call it shortly as MLP. This is MLP. So for each layer, for each neuron, you will have one bias. This is a bias neuron. This is a bias neuron. The input for bias neuron is always minus 1. Okay, remember that. And you can check the weight for this bias neuron W0 as you wish, along with the weights to the next one. So here, the table size, the structure data size with how many features are there here? How many columns will be here? A1, A2, A3, A4, A5. So this is the, and this is the target. Why this A5? Why it is not A4 or A6, A10? Anyone? Anyone? Anyone respond if you understood? Otherwise, this deal is very complicated. Remember that. Hey, unless you follow this teaching, you can't do anything with this. There is no use for your future. You guess something, that may be wrong, that may be right, no problem, no issue. Why I taken only 5 columns in my data set? Are you there or just connected and left from the class? So I call you one by one.
Your input layer is 5 year having also.
Okay. How we decided? Based on this, we decide this table, or based on the data set, we decide this network. Which one we decide? Madam, class లో ఉన్నా 5 minutes. ఏమంటారు? So this is one thing, right? But here, based on the data set availability, you have to create your own network. This may be anything, any number of neurons you can check as you wish. This is also as you wish you can check. Okay, sorry, hidden layers. Output layer generally depends on the number of values, discrete values involved in this. Suppose it is a, when you use this one, three neurons, this data set has a three classes like yes or no, can't say, okay, okay, 0, 1, 2. Okay, those values repeated any number of times here. So that type of classes exist, then you can use more number. Suppose it is a only binary data 0 and 1 as an output, yes or no, then you take only one neuron here. In this neuron, the activation function is always sigmoid function for binary class data, and more than two classes we use softmax function. So anyhow, here also at each neuron, you have to take either any activation function, sigmoid function, or ReLU function, SeLU functions, whatever it may be, have to take here. So these number of neurons in the input layer depends on the number of attributes involved in your available data set. So here, if I use only 5 columns, 5 features in my data set, you create the network starting with fixing with 5 neurons, input neurons for your layer. So here there will be no activation function in input layer. Remember that whatever this data feeds here, suppose this A1 goes to this one goes to this one goes to this, and like this. Okay. So this now I fed only the first input object, and this transforms, simply transforms the input data to the neurons by weighted sum. Okay, that's why here there will be no activation function used. Okay, but in hidden layer and output layer, we should use, okay, activation function. So this activation function again depends on the complexity of your network and the data, and based on the requirement, you have to change this activation value. I told you one requirement here is when you have a binary, you should use the sigmoid as an activation function in output layer. If you have more number of classes, you should use softmax function in the output layer. In hidden layer, not only one hidden layer, there may be so many hidden layers. Okay, based on your wish. Okay, you can construct your own network, and in this there may be 3, 4, 5 neurons in the next hidden layer. This is a H1 hidden layer 1, hidden layer 2. This is the output layer. Okay, this is the input layer. In input layer, except this input layer, in all layers neurons have the activation function, and in input layer there is no activation function. Remember. So here, what is a perceptron here? When you use each neuron as a perceptron, you should use a step function here. Okay, if it is not a step function, you can use any other function. Okay, so each if you use a step function in each neuron and any hidden layer, each neuron becomes as a perceptron. Okay, remember that. So in multi-layer feed-forward neural network, if you assume this, if there are one input layer and hidden layer, hidden layer, one output layer. And what is the process generally occur in each hidden neuron and the output neuron? So this is the process occurred. It takes a weighted sum from the input data and it feeds this weighted sum to the function activation function by adding this bias value also, and it gives you the output. This is the procedure. So how to propagate the inputs forward? So for J, always you check Jth is a Jth is present layer or present layer neuron. Ith is the previous. Okay, that means here. Suppose if I'm talking about this one. This is the jth layer neuron, and then it is treated as ith. It is treated as kth. Remember, that's why it is output k. It is oj, and these are all i's. Okay, so how to calculate the input for any jth neuron? Already we have seen this. Wij oi. Oi is the output from the input layer. So this is the previous layer output. So that is nothing but whatever you feed it, that will be the output here. That is denoted with OI and multiply with the corresponding weight. Okay, like this, all the weights who are suppose here, if you want to feed the weighted sum here, there are four connections: 1, 2, 3, 4. So you will be there will be four weights and four inputs are there. Multiply with the weights with the inputs and make it sum and feed it to this neuron. And in this neuron, there will be one activation function, and that activation function gives you output as this OJ. This OJ again becomes the inputs to this one. So this OJ, this value, this. So here there are three connections here. So the output from this hidden, the output from this, the output from this. Again, you multiply this output with this weights. Okay, this output with this weight, and this output with this value. So this is a weighted sum again as a input to this neuron. This is the feed forward nature. Suppose when you use this activation function as this 1 by 1 plus e power of minus a, this is called the sigmoid function. That means you got this output at a jth neuron by checking the weighted sum. Okay, like this, minus of ij. Ij is a weighted sum at ith neuron, jth neuron. So this weighted sum will be fed into this formula 1 plus e power of minus this weighted sum. Gives you some value. That value is a output at that neuron. So this is denoted with OJ. So now it is okay. This is the procedure until then we get the output here. When this output is not equal to the original output value for any input, okay, this is the input first row and its corresponding, suppose it is 10, but when you feed this row with how many one to okay en attributes are there, whatever it may be, when you feed it to this neuron here, and when you got the 10 when you get the predicted value as per this procedure, and suppose 8, what happened? This is 8 is the predicted value. We denoted it as oj yj, or this is the oj at the output layer, or ok at the output layer. So this ok should be equal to this target value in the data, okay, table. But if there is a difference here, then you need to update the weights. How to update this weight between ith neuron to jth neuron? You'll get this learning rate like a eta into error between these two and this OJ. How do you calculate this error here? The calculation of the error depends on two factors. One is at the output layer, one at the hidden layer. Suppose if you check this error J here, suppose if you want to calculate this J error at this neuron, here you take this output of this one into 1 minus this OJ, whatever you got as an output at this neuron, and weighted sum of error K. So how many connections are there? These connections are there, and the weight errors of the previous next layers, and multiply with the weights, corresponding weights, you will get this error J at this point. Okay, the same thing you can apply at the output layer also.
I initially planned for that.
Called theta j. So at present, layer with another OJ or OK connected to two neurons. Okay, this is the procedure of feed forwarding. All right. How to get the updation of the output is called the backward. This is the feed backward procedure to update the weights. And once these weights updated from this right to left up to this one based on these formulas, two formulas, and when you updated all these weights, again you feed the next record to this network again. Okay. So after feeding this one, again you will get some output. Again you check the corresponding output. If there is a difference, again you update the weights. Like this completion of the entire data set in your training training data set, you have to repeat so many times to update the weights until you get the exact predicted value equivalent to the target value. Okay. This is the algorithm for this multi-layer perceptron. The same formulas I used here how to update. Okay, you can go through this one. And when you have to terminate this training process, when all delta WAJ in the previous epochs were so small, that means nearest to zero, to be below some specified threshold, if the experts fix some threshold value, or the percentage of the tuples, okay, misclassified in the previous epoch is below some threshold value, then you can stop it. Or a pre-specified number of epochs has expired. Just I want to uh, try my network only 100 epochs. So 100 epochs has completed, then don't go further. So that type of preconditions, based on the preconditions, you have to terminate your trading process of your model. This is one of the example. All of you, take the snap of this one and let me know. Have you taken account? All of you take this snap. Completed. Tell me whether you completed or not.
Yes, sir.
Right. Now, using this, what happened here? What is the output? Target value, original value? The original value for this input, the input is A1, A2, A3. Three columns are there here. Okay, this is the first input. What is that first input? 1, 0, 1. And this target data for this input is 1. This is 1 here. And the weights given, the network has given, this is W14. What is W14? From 1 to fourth connection. This is the fourth connection. This is equal to 0.2. So 1, 5. This is minus 0.3. It is again 2, 4, 0.4. Like this, you fix it on this network and update the weights at one iteration. Okay, that means you just feed these values into the network and update use these weights, initial weights already given, and these are the bias values. That means have to connect with this one. This is the bias neuron connected to this. It is called theta 4, and always the input is 1 and the weight is it is minus 0.4. And again, this for this 5, this is 0.2, just 0.2. And here one bias neuron will be there. This is also another theta 6 here. The theta 6 weight is given in this as 0.1. So it is a 0.1. It's like a weight. Okay, bias weight W0. Here we use theta. So based on these formulas, all of you check this also. This form, what is that? Formulas. All of you check this snap also. Using the below formulas, okay, you try to update the weights of the network here and give me the weights, updated weights from here to from here to these weights using the above formula. Okay. Anything required here? Learning rate I given as 0.9. It is like a eta or L. Sometimes we use L. Have you taken these formulas? All of you respond.
Yes, sir.
And try to update the weights and let me know these weights after completion of your completion. All of you start calculating the weights using this network now. All of it calculate. So who are the absentees? Sindhuja, you just text me in WhatsApp who are the absentees. Show this.
One second now.
So is number 2, 1 is absent, right? 1, 1, 14, 15.
Yes,
Okay.
I messaged you.
Okay, 3 members were absent. Okay, complete it and keep it with you. Okay, I will ask the questions in the next class. Okay. So I'm closing here because I have some other work in R&D.
You need to cook.
Okay.
If you have any doubts, you please call me and you can clarify the doubts.
వీటి ఇట్లా అయిపోగానే నేను ఫస్ట్ వాడి కాల్ కట్ చేసి వైఫై కనెక్ట్ చేసి
Can you send the PPT, sir?
Who is this? Sindhuja?
Yes, sir.
Sindhuja, you are not a BTech student, even intermediate student. Okay, you should not read the PPT. You should read books, reference books, so that you will get more and more clarity. Okay, try to